Hello everyone. I'm going to do two examples of how to use our sum or difference identities as a way to find the exact value for some trig functions. Now these are nice because they give us a way to find the exact value when we're dealing with an angle that isn't one that we normally see on the unit circle. So for example, I have the cosine of 15 degrees and the sine of 5 pi over 12. Both these angles, they're not one of the standard ones that are on the unit circle, but using our sum or difference identities, we can still find their exact value. So to do that, what we want to do is we want to rewrite the angle in terms of angles that we already know, ones that are a part of the unit circle. So that would be angles that are multiples of 30, multiples of 45. So you have like 30, 60, 90, and so on. Or you have 45, 90, 135, angles like that. Or with radians, you want to try and work with angles that are multiples of pi over 6, or angles that are multiples of pi over 4. Okay? So starting with the cosine of 15. If I look at 15, knowing that I want to rewrite this in terms of angles that are either 30 or 45, the first one that comes to mind, 15 degrees, this is the same as 45 minus 30. So using two angles that we know, I can write this as a difference. And now that this is expressed as a difference, I can use one of my identities, and I can expand this out. So using our difference identity for cosine, okay, this is alpha, this would be beta. So we have the cosine of alpha times the cosine of beta plus the sine of alpha and the sine of beta. So here, these are all angles that we do know how to evaluate. So because these are ones that are on the unit circle, we can substitute in the values that we know, and then we should be able to do some simplifying. So let's see, so the cosine of 45, this is the same as the square root of 2 over 2. The cosine of 30, so this is the square root of 3 over 2, and then plus the sine of 45, that's the same as the cosine of 45, and then the sine of 30 is 1/2. All right, so we can multiply our fractions together. When we multiply two radicals, we can multiply their radicands, so what's underneath. So the square root of 2 times the square root of 3, that's the same as the square root of 6. And that's actually going to be over 4. And then here we have square root of 2 times 1, and then 2 times 2 in the denominator, so this is the square root of 2 over 4. We have the common denominator, so adding these fractions, so the exact value of the cosine of 15 is the square root of 6 plus the square root of 4 over 4. And that is the exact value. So exact value meaning it's not rounded at all. This is exactly the value for this x value. Okay. Take a look at the second one here. The sine of 5 pi over 12. So this is, it's pretty close to pi over 2. It's pretty close to half, but not quite. And there may be multiple different ways we can do this, but just thinking about how we can split that up. Again, in this case with radians, I want to use things that are multiples of pi over 3 or pi over 6, or things that are multiples of pi over 4. So if I split this up, So I'm going to take 5, and I want to split that up into 2 parts here. So if I do 3 pi over 12 and 2 pi over 12, taking 5 and I'm just splitting it up into 3 and 2 basically, but I know 3 over 12 simplifies and 2 over 12 simplifies. So this is the same as the sine. 3 over 12 is pi over 4, and 2 over 12 is pi over 6. And those two angles, those are ones that are common on the unit circle. So now we can use our sum identity, because we have it written as a sum of two angles. So we'll use the sum identity for sine to calculate our exact value. So that looks like, so it's the sine of alpha, so our first angle. So the sine of pi over 4, the cosine of the second angle, and then plus, and we flip-flop that, so the cosine of the first and the sine of the second. Now each of these, we can find the value for each of those and then do a little simplifying to get our answer. So let's see, the sine of pi over 4, the square root of 2 over 2, and the cosine of pi over 6, that is the square root of 3 over 2. Cosine of pi over 4, the same as sine, and then the sine of pi over 6, that is 1/2. Well, that looks very familiar to what we have over here. So same thing, multiplying the radicands, square root of 6 over 4, multiplying here, square root of 2 over 4, and we actually end up with the same exact answer. Which is not too surprising. If I were to rewrite the cosine of 15, if I rewrite that in terms of radians, cosine 15, that's the same as the cosine of pi over 12. 15 is half of 30, so half of pi over 6, we get the cosine of pi over 12. And the cosine of pi over 12, we see that that is the same as the sine of 5 pi over 12. But that makes sense. This is a perfect example of our cofunction identity for sine and cosine. These two angles are complements to each other. If I add them together, pi over 12 and 5 pi over 12, we get 6 pi over 12, which is pi over 2, which is 90. So because these angles are complements, and sine and cosine are cofunctions to each other, these do have to equal each other. But anyway, here's two examples of how to use our sum and or difference formulas, our identities. And as I said in the beginning, the big idea, what you're trying to do is you want to take your angle and you're going to rewrite it as a sum or a difference of angles that we do know how to work with. So multiples of 30, multiples of 45, multiplies of pi over 6, or pi over 4.